Hi everybody, welcome to Year 5 Maths for Week 2, Term 4. This is Lesson 1 and this week we are looking at data again. So today we are just looking at line graphs and interpreting line graphs. So today we are learning to interpret line graphs. Now this word interpret is not just about reading a line graph and being able to read it, it's also about explaining the meaning of the line graph. So really looking for what's the important information in this line graph. What is it telling us about the data, for example? So looking for the key bits of information and also the overall picture. So what is the meaning of this graph? To do this, you need to read the title of the graph. So most graphs should have a good, meaningful title, which tells us, what this data is about, what this information is about. Then next thing you want to do is look at the x-axis, which is the horizontal axis, and the y-axis, which is our vertical axis, so going up and down. This will tell you how the data has been measured. So whether you're talking about money, so it might be measured in dollars, or it might be measured in US dollars or yen, Japanese yen. It might be temperature, it might be in Fahrenheit, or it might be in Celsius. You really need to look at both of these axes to see how the data has been measured. Next thing you want to do is check the axis scale as well. So particularly with data where the numbers are quite large, it's not just going to go 1, 2, 3, 4, 5 for each of the intervals. It might jump by hundreds or thousands or millions. So you need to look at what the scale is. What does each interval on the scale mean? And lastly, we're going to look at checking whether there are no missing values. If there are missing numbers or values on an axis, it's going to change the shape of the data and it can actually mislead somebody who's reading it or kind of tell them something that's not actually happening. Okay, so let's review the features of a line graph. So this is what they look like roughly. The first thing I'm going to look at is my title. So this is about yearly bike sales. So this is what this graph is telling me. This is the data or the information this graph is telling me. The next thing I want to look at is my x-axis, which is my horizontal axis, and my y-axis, which is my vertical axis. And I can see that each of them has a label. So my x-axis is years, and my y-axis is number of bikes sold. So they've got these labels on here, which is excellent. Also, I can tell this is a line graph because it's got these points, which are called data points, and they line up with the years and the number of bikes sold. And each of the data points is connected by a line. So it's connected by this kind of peach color line, and that shows me the shape of the data. And it kind of shows me a trend, whether things are increasing, whether they're decreasing, or whether they're staying the same. Okay, the next thing I want to do, once I've identified what data is in my x-axis and my y-axis, or how the data is being measured, I should say, I want to look at the scale for each of those axes. So the x-axis, it's a scale of one interval. So these are the intervals, basically where the lines are and where the labels are, is 1 year. So 2010, 2011, 2012. But on my y-axis, I start from the point of origin, which is 0, and it goes up by 100. So one interval equals 100. And we're talking about number of bikes sold. So it's 100 bikes, 200 bikes, 300 bikes. And that's my line graph. So now I understand the line graph, I can actually start interpreting it, finding out what the main meaning behind this graph is. Now, overall, you could say, well, the main story or the main meaning in this graph is that yearly bike sales have increased between 2010 and 2012, and they continue to go up into 2013. Okay, to start off with, we're just going to look at reading a line graph to answer some questions. And then the next couple of examples, I'll go through interpreting and making some statements about the data. So this is emails Susan received. So Susan was working in an office and she recorded the number of emails she received each day and put it on a line graph. So here, that's my title here. my x-axis, I've got the days of the week, and on my y-axis, I've got emails. Now I can see the scale on the x-axis. It's every day basically. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, assuming she works 7 days a week. And it doesn't skip any day. So it's just, each of these intervals is 1 day. Same on my y-axis. It starts from 0, goes 1, 2, 3, 4, 5, etc. So it's just going up by 1. So there's no scale there, it's just a one-to-one correspondence. Okay, my first question, on which day did Susan receive the most emails? Well, I look at my line graph. I go to my y-axis because that tells me the number of emails. Here, 8 is the highest value, and it was on a Monday. So Monday. On which day did she receive the least emails? Well, I want to go to my lowest value, which is down here. It's Tuesday. How long is this time period? Well, I want to look at my x-axis because this is to do with time, whereas my y-axis is to do with number of emails. So it starts from Monday and ends on Sunday, so it's 7 days or a week. Susan's emails decreased from Thursday onwards, true or false? So let's go to Thursday, which is here. I go up. And I can see that they're getting smaller, which we know is decreasing, so it is true. On which day did she have the biggest increase in emails received? So this is where I need to look at the shape of the data. So which day did she have the largest increase in emails? So here I'm looking at this point here because this is going up and it's the steepest. So here we started at 0, and then on Wednesday she had 5 emails. So there's a difference of 5, and that's the greatest increase she had. This one here is 5 to 7, which is 2, and all the other ones are decreases. So it would be Wednesday. And lastly, what was the total number of emails Susan received? Well, all I need to do is just add up each of these data points. So 8 plus 0 is 8, plus 5, because here I go across is 5, 13, plus 7 is 20, plus another 6 is 26, plus 3 is 29, and plus 2 is 31. So she received a total of 31 emails in that week. Now today, for most of your activities, you'll be answering questions similar to the ones we just did, but I also want to show you how to interpret data, how to interpret a line graph and kind of find the main pieces of information in it. So the first thing I'm going to do, I've got a line graph here, is I'm going to look at my title. That's always the first thing I do. This is sunflower growth, and it's between the 30th of July and the 29th of August. Okay. The next thing I'm going to do is check my axes. So my x-axis is days, and my y-axis is height in centimeters. Okay, so I've checked the title, I've checked the axes, what they are. Now I want to look at the scale of each of the axes. Now this is where it's a little bit trickier than the last one, because here I've got Saturday, but then I've got Monday and Wednesday and Friday. So it's skipping every second day. So these are intervals of 2 days. So that's the scale on the x-axis. And on my y-axis over here, I can also see it starts at 0, but it's going up by 2s. So 2, 4, 6, 8, and so on. So again, the scale here is 2. So this is 2 centimeters. Each interval is 2 centimeters. Okay. Now the next thing I want to do is just look at the shape of the data. What is the shape of this line? Well, I can see that the line is increasing. It's getting higher from its starting point here, and it's not going down at any point. So it's just increasing. So overall, the sunflower is growing. It's not getting any shorter. Okay, so the first thing I'm going to say here is between the 30th of July and the 29th of August, because that's my start point and my end point, the sunflower grew 20 centimeters. So here, at my endpoint on the 29th of August is 20 centimeters, and it started off at 0, so the difference between 0 and 20 is 20, so it grew to 20 centimeters. For the first 6 days, the height of the sunflower did not change. So here, remember, this is intervals of 2, so 2, 4, 6, it's still at 0 when it's got to Friday. So that's the first 6 days. It's probably a seedling, just ready to burst. For those first 6 days, it hasn't grown. Between the 5th of August and the 13th of August, the sunflower grew at the same rate. So I've got this line here, which is a nice straight line, which kind of tells me, okay, well, there's a bit of a pattern going on here, a linear pattern, because it's a nice straight line. So it's going up by 2s. So on Sunday, it was 2, then 4, then 6, then 8. So each day, or every 2 days, it's grown by 2 centimeters. So it's a linear pattern, so it's growing at the same rate there. From the 23rd of August to the 25th of August, the rate of growth increased by 1 centimeter. So here, this little bit here, it's actually gotten quicker at growing, because this is a steeper line than this line here. And I can see that it's even gone up 3 centimeters. So here I've got 14. And because this is in between the 16 and the 18, it's 17. So it's actually a difference of 3 centimeters between those two data points. And from the 27th of August, the rate of growth appears to be slowing. So from the 27th here to the 29th, it's only grown by 1 centimeter, because this data point is between 18 and 20, so it's 19. And on the 29th, it's 20, so it's only a 1 centimeter difference. So it seems like the sunflower is starting to slow down its growth, and that might be its final growth. It might only get to 20 centimeters. Okay, let's look at another example. So here we've got Elf the puppy's weight. So that's my title, and I've got a line graph. So the first thing I'm going to do is look at my x-axis, and I can see here this is months, and my y-axis I've got weight in kilograms. Now each of these have a scale of 1-to-1 correspondence. So here I've got October, November, December, January. So it's just 1 month is for each of these intervals. And the same with the y-axis. I start from 0, 1 kilogram, 2 kilograms, 3 kilograms. So each of these intervals represents 1 kilogram. So it's just going up by 1s. Okay, I'm going to look at just the shape of the data to start off with before I even start making any interpretations of it. I can see the shape, it starts at 8 and it starts to go down, which tells me that Elf is losing weight. His weight is going down each month. But then suddenly it kind of jumps back up again, and then it goes down and then gradually increases again. So he kind of has this interesting weight loss journey where he loses a lot of weight and then starts putting it back on again. Isn't that too familiar? Okay, so let's make a few statements about this data. So firstly, between October and July, Elf lost 2 kilograms. So we started off with October at 8 kilograms, and the end point is July, and he's got 6 kilograms because I just tracked that across. So overall, in this whole time period, he's kind of really only lost 2 kilograms because he's put on this weight in this kind of second half. Between October and March, Elf lost 5 kilograms. So here, I'll use a different color. October was 8 and March is 3. So the difference there is 5. So he lost 5 kilograms, which is his period of kind of weight loss. From May onwards, however, Elf's weight started to increase at 1 kilogram per month. So even though it kind of spiked up here again, but it went down again, I thought, let's just look at the main story here. His weight has started to gradually increase again. So this might have been a bit of an anomaly. It might have been like, oh, he's just eaten too much for 1 month or hasn't had enough exercise, but maybe he's going to lose the weight again. He did, but then now it's gradually creeping up again. So I thought I'd make a point of that. And Elf's lowest weight was 3 kilograms in March, and his highest weight was 8 kilograms in October. So uh, even though he's starting to put weight back on again, he's still lost weight, and he's lower weight than his highest weight, which was in October at 8. Lastly, I'm just going to look at checking graphs for their accuracy to make sure that they match the original data that they come from. So here we've got a line graph, and it's about temperature. I can see in my y-axis in Celsius, and then it's over months. Now I can see it's January, February, March, and this table here is the source data. This is where the data for this line graph comes from. And if you looked at this straight away, you might be thinking, okay, yeah, it makes sense. Yep, so it sort of goes up here and then it peaks in August and it goes back down in December. But actually, if you look closely at the scale, you can see that the month of June is missing. It goes May, July, where we know it goes May, June, July. So that's a point where the scale or the y-axis, the scale of the y-axis isn't actually correct because we're missing an interval. So here we know that June would be 16 degrees, so it would be like here. So make sure that you check that each of the axes are done to the right scale and there aren't any missing values. I'm just going to check with the y-axis, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, so there's nothing wrong with the y-axis. The other thing to look out for is just to make sure that this data here in the table matches what's being shown in the graph. So let's say we go to the month of July. July, the temperature is 20. Well, let's go to the July here. And if I go up, they've actually plotted it at 16. So the July temperature should be here. So again, another inaccuracy or mistake in this data. So today in your activities, you'll have one question where you need to go through and look at the graph and spot the mistake. See where either there are missing values or the data doesn't match up to what's being shown in the table. Okay, so just the main ideas from today. Interpreting means explaining the meaning of information or data. So it's not just about reading it, but also looking for what's the main story of the data. What's the main thing this data or this information tells us? Is there a pattern? Is there a trend, for example? Does it increase or does it decrease? Or does it go up and down? You also want to look at the highest and lowest points as well when you're describing and interpreting the data. And then always when you're reading and interpreting a line graph, firstly, always read the title, read the X and Y axis. This is even before you start trying to make sense of it. Identify the scale on each axis. So for example, if an interval equals 5 years, if it equals 2 years, and then check for any missing values on the axis as well to make sure that it's accurate. All right, good luck guys. I'll see you tomorrow for lesson 2. Bye-bye. Welcome back everybody. This is lesson 2 for Year 5 Maths. We're on a Tuesday now, and today we're looking at interpreting and describing data with a focus on finding totals, and I'll explain that in a moment. So today we are learning to find the total number of data values in column graphs and dot plots. Now, when we're talking about the total number of data values, that's talking about how much data is contained in that data display, in that graph or in that dot plot. So for example, if we surveyed some students and we put that into a data display, the total number of data values would be how many students did we survey? Or if we had data on sales at a shop and it was in dollars, the total number of data values would be what was the total amount of sales that's shown in that data display. Okay, so today you need to identify and add all of the data values. So it's about reading a column graph and a dot plot and adding all of those values together to get your total, but then also recognizing where a graph has a scale as well, because that will change your total. Okay, let's look at dot plots first. So here I've got my title, which is favorite candy in 3A. So a student or a teacher has surveyed the students in this class about their favorite candy. Now on my x-axis, I can see the candy options, Kit Kat, M&M's, Skittles, Snickers, and Starburst. And on my y-axis here, I've got number of students. Now for a dot plot, I don't actually need to have a y-axis because the dots are actually a count of how many students preferred that candy. So here I've got Kit Kat, 1, 2, 3, 4. So 4 students liked Kit Kat, 8 liked M&M's, 2 liked Skittles, 5 liked Snickers, and 1 liked Starburst. Now to find the total number of data values, all I need to do is just to add these numbers together, and that will give me the total number of students that have been surveyed and the total number of data values. So 4 plus 8 is 12, plus 2 is 14, plus 5 is 19, plus 1 is 20. So there are 20 students. It's going to put ST, and that's my total data values there. Now this changes where we have a scale in play. So let's look at this dot plot over here. Now this is favorite candy for stage 2. Now usually we use dot plots where there aren't too many data values in altogether. So you wouldn't want to have to count 100 dots up or 1,000 dots because it really is quite painful. You'd probably use a different type of data display, probably a column graph for that. But for small numbers, dot plots are quite useful. But we can also use a scale. So here, I see I've got this situation where I've got a half circle. And if I keep looking around my data display, I can see down here a circle equals 2 students. So where I have a half circle, it's going to equal 1 student. Now, when I'm adding up these data values, I should say, for each of the candies, I need to make sure that I double it. So here I've got 7. 7 times 2 is 14, or I could count by 2s, 2, 4, 6. Here I've got 6 plus 1, because the half is 1, so I've got 7. I've got 4, and again, I have to do that because it's the same as the Skittles, so it's 7. And then I just need to add them together. So 14 plus 6 is 20, plus 7 is 27, plus 4 is 31, plus 7 is 38. So 38 is my total number of data values. It's that simple with dot plots. So just make sure you're checking the scale if there is one. Otherwise, you can assume that each of these represents one person or one thing, whatever is being described by the data. Okay, now onto column graphs. Here we've got number of pets in 5M. Now, it's interesting, this graph, because you might think number of pets, oh, okay, so this is how many students have cats and how many have dogs. Well, actually, the title of the graph is saying number of pets. So a student might have, 5 dogs or 3 cats. So it's really just asking students how many pets of each of these kinds they have, and then just adding them up in each of the columns. So here I'm going to go to cats, because I've got my pets here on my x-axis, and now I can see on my y-axis it goes up by 2s, and I can see it's halfway between 10 and 12, so it's 11. This one here is halfway between 6 and 8, so it's 7. Here it's right on 12. Here it's on 8, 2. Here it's on the line for 6. And here it's halfway between 0 and 2, so it's 1. And again, just to find the total number of data values, all I need to do is add these up. So the total number of data values would be the total number of animals or total number of pets that all of the students in 5M have together. So here 11 plus 7 is 18, plus 2 is 20, plus another 10 is 30, plus 8 is 38, plus 2 is 40, plus 6 is 46, plus 1 is 47. So we're talking about 47 animals altogether, and that's the total number of data values in that data display. Now, sometimes it will tell you, the total number of animals, but other times you'll just need to add them up. It really depends on who's put together the data. But the good thing about this is now you can actually see the total number. You can actually make statements about a particular type of pet as a proportion of the total number of pets. So here I can say that reptiles represented 1/47th of all pets in 5M, or dogs represented 7/47ths of all pets in 5M. Or I could divide 7 by 47 and times it by 100 to get a percentage. I'm not going to do that right now. But that's why it's quite useful to know the total, is you can actually show one particular value, like dogs or birds, as a fraction of the whole number, which is 47. So really today, all you need to be concerned about is being able to add up each of the data values for a dot plot and for a column graph. Okay, so the main ideas from today: when we're trying to find the total number of data values, identify the value for each piece of data. So for example, there are 11 cats, 7 dogs, 1 reptile. Check if there is a scale, because that will change how you read the data, particularly with dot plots. Add all of the values together to find the total number of data values. And then once you have the total number of data values, you can represent a category as a proportion of the total. You don't need to do this today, but I'm showing you why it's useful. So for example, with cats, we had 11 cats and we had 47 pets in total. So in the class 5M, cats represent 11/47 of pets in 5M. There you go. Nice and simple. Now, your questions today, they're not all about finding the total number of data values. That would be quite a punish. So it's also about reading the different graphs and finding the difference between different points in the data display. All right, good luck today, guys, and I'll see you tomorrow for Wednesday's lesson. Bye-bye. All right, welcome back to Year 5 Maths for Week 2, Term 4. Today we are looking at data, but more particularly relationships between different data values. Okay, so today we are learning to identify and describe relationships in data displays. Data displays are any way of showing data. So it could be a table, it could be a line graph, it could be a column graph, it could be a dot plot, any way of showing data. So to start off, we need to identify related numbers in data displays. So for example, if we have an 8 and a 2, we know that 8 is the same as 2 times 4. So that's a relationship, a numerical relationship between those two numbers. Then you need to describe the relationship. So for example, if 8 people liked swimming and 2 people liked basketball, then we can say 4 times as many people prefer swimming to basketball, because we know about that numerical relationship. And there we've got a relationship there that 4 times as many people prefer swimming to basketball. So let's have a look at a few examples now. So let's start off with a column graph. So here I've got the title, which is Riverdale High students' favorite sport to play. So they've chosen one sport, and I can see the sports are listed as categorical data on the x-axis. So they're the categories. On the y-axis, I've got the number of students, and the scale is going up by 20s. So 0, 20, 40, 60, and so on. Now, I don't really need to use the y-axis so much because I've got these data labels at the end of each of the columns. So for athletics, it's 15, for basketball, it's 50, and so on. But it does show that it's in scale, that each of these are proportional to one another. Okay, so now let's think about some relationships. Well, I can see that all of these numbers are either end in 5 or 0, so they all have a factor of 5 at least. Now let's think about some of the relationships. I'm going to start with soccer because soccer's the most popular sport at Riverdale High. 200 people chose it. And I know immediately, well, I've got 10 down here and I've got 200 up here. Well, I know there's a relationship there that 200 is 20 times 10. So I can already see one relationship between these two values, but let's look for some more. So let's start off with soccer. Here are some relationships that soccer has. So it's 20 times more popular than swimming. It's 4 times more popular than rugby because rugby is 50. So 50 times 4 is 200. And same with basketball. So 50 times 4 is 200. So it's 4 times more popular than either rugby or basketball. And I know that tennis is 25 and 25 is half of 50. So it's actually going to be 8 times. 8 times 25 is 200. So soccer is 8 times more popular than tennis. Let's go to netball now. Netball is 150. And I'm going to go to athletics again. 15 times 10 is 150. So it's 10 times more popular than athletics. I can go to swimming now. It's 15 times more popular than swimming. So I can just do switch those numbers around. I can say it's 3 times more popular than either rugby or basketball because we know those are 50. So 50 times 3 is 150. And because tennis, again, is 25, which is half of 50, I can say it's 6 times more popular than tennis. So 6 times 24 so 25 is 150. So there are some of the many relationships I could find in the data. Now this data I've just put together to make it nice and easy to find the relationships. Generally speaking, in a column graph, you won't have so many, so you will need to look, but it's about looking for those relationships between the numbers, knowing that, 25 times 2 is 50, for example, or 50 times 4 is 200. So we can say 4 times more people like soccer than they do rugby. Let's look at a line graph now. So here I've got a title which says the average day and night temperatures in New York City. And I can see on the x-axis that it's over a year, and the x-axis, each of these intervals is 1 month. So it starts in January and goes all the way to December. Now I have checked, there are 12 months there, so there's no missing data. And on my y-axis, it's got the temperature, and this is in Celsius. It doesn't actually say that here, but a good graph would have a data label, but I've checked this one. So here it goes up by 5 degrees at a time. So it starts from 0, it goes up to 5, but it also goes below the line here as well, because you can have negative temperatures when it gets -5, -10, and it starts to get really cold. Here we've got 2 lines as well. We've got one for day, which is red, and one for blue, which is night. Now, this is a bit trickier than the column graph because we haven't actually got the data labels at the end of each of the points, and I don't even have a horizontal line to kind of track across where things are. I actually had to use a ruler to do this myself, but here are some of the relationships that I found. So on average, because remember these are average day and night temperatures in each of these months throughout the year, July is 6 times hotter in the day than March. So I go to my day line, which is red, and I go to July, and the temperature is 30 degrees. And in March, it's 5 degrees. That's the average day temperature. So I know that 5 times 6 is 30. So I can say that July is 6 times hotter in the day than March. I could also say that March is 6 times cooler in the day than in July, if you wanted to do it that way. Days in March are 1/5 of the temperature of days in June and September. So here we've got days in March are 5 degrees, and in June and in September, it's 25 degrees. So I could say that June and September days are 5 times hotter than days in March, but I can also represent that as a fraction. We'll go, well, actually, if that's the case, then 1/5 days in March are 1/5 the temperature of days in June, because 5 times 5 is 25. So that's another way I can represent that relationship. If you just wanted to say, days in June are 5 times hotter than they are in March, that's totally fine as well. It's just another way of thinking about it using inverse operations. Nights in May are half as hot as nights in July. So now I'm going to my blue line. I've got July here, which is 20, and May, it's 10. So I know that half of 20 is 10, so I can say nights in May are half as hot in July, or I could say nights in May are twice as cool as they are in July, or I could also say July nights are twice as hot as they are in May. So again, I'm looking for these relationships, and they're usually based on multiplication and division. This is the last one here. This is not so much about a relationship between two different numbers. This is just about finding similarities. So this is another way you can find relationships. May and October have the same day temperature approximately, which is 15 degrees. And I kind of found that quite interesting because it sort of shows in this time 1, 2, 3, 4, 5, in that 5-month period, it kind of goes up again and then it goes back down to about the same average day temperature. Sorry, I was looking at the night temperature there. The day temperature would be here. There we go. So it goes up here and peaks in July, then it goes back down to the same average day temperature in October as it was in May. So I found that quite interesting and a relationship worth noting. Okay, let's look at a dot plot now and some of the relationships we can find in this dot plot. So here we've got time spent on homework per week in 7G, which I assume is a high school class. And down the bottom here on the x-axis, I should say, we've got hours spent. Now I don't need to have the y-axis because I can assume that each of these dots represents one student because there is no scale telling me otherwise. Now I've added all of these dots up and I know that there are 24 students in this class, or at least 24 that have been surveyed. So here are some of the relationships I found. So firstly, I found that half the class spent 3 or less hours on homework per week. So what I did was I counted up all these values here between 0 and 3, and it was 12. And I know that 2 times 12 is 24, and 12 is also half of 24. So I can say half the class spent 3 or less hours on homework per week. But I can also say that a quarter of the class did 1 or less hours per week because we've got 1 person doing 0 hours and 5 people doing 1 hour, so that's 6. 6 times 4 is 24. So 6 is 1/4 of 24, 1/4 of the class. At the other end of the spectrum, I can also say that 1/4 of the class did 6 or more hours per week because here I've got 6 students as well. For 6 all the way up to 9 hours, that also represents 1/4 because 6 times 4 is 24. Now, there's other relationships you can find here. They're not so meaningful. You could say that twice as many students spent 2 hours on homework, so that's here, as students who spent 8 hours on homework. That you can find lots of different relationships here, or you could say, 5 times as many students spent 1 hour than spent 0 hours. It's probably not so relevant though. I think it makes more sense to kind of split the class up this way into halves and quarters because it gives you an idea of what proportion of the class is spending a lot of time on homework and what's spending not very much time at all. Okay, and lastly, let's look at a table. So here we've got Cosmic Comics and their September sales for 2021. In this column, I've got the title of the comic, and this column is the number of copies that were sold. Now, this has been arranged from the most comics sold to the least comics sold. So Batman had 58 compared to Iron Man, which was the least popular, had 7. And here down the bottom, I've got the total, which is 225 comics. So let's look for some relationships. Well, firstly, there are some simple relationships I can find here. I know that 7 and 14 are related because 7 times 2 is 14. 21 and 7 are related. 28 and 7 are related. 7 times 3 is 21. 7 times 4 is 28, and so on. So I could say 4 times as many people bought Superman than Iron Man because 28 is the same as 7 times 4. I could also say a whole lot of other relationships between these numbers. Another way I can also do things is I can say together, Spider-Man and Iron Man represent 1/5 or 25% of sales. So here I've got Spider-Man, which is 38, and here I've got Iron Man, which is 7. When I combine those two together, I get 45, and 45 times 5 is 225, or 225 divided by 5 is 45. So these two comics, when we combine them together, represent 1/5 of the total comics sold. So that's another way you can look at relationships, is you can combine different categories or different data together to come up with a proportion of the total data. A Batman accounted for approximately 1/4 or 25% of sales. Now it's not exact, so 225 divided by 4 isn't 58 exactly, but it's roughly the same. So we can say it accounts for approximately 1/4 of all the sales. That's information that's quite useful to the person who's running this comic book shop. So they know, well, I need to stock more Batman comics, and that's, my biggest seller in September was Batman. It accounted for 1/4 of the sales. Another way I can look at things is just look for similarities. Here I've got Wonder Woman, Avengers, and Superman, and they all have similar sales, so 30, 29, and 28. They're very similar, so I can just make a statement that they have similar sales. That's also a relationship. So today it was all about finding relationships in data. To do this, we want to look at, firstly, numbers that are related. So there might be factors of one another or multiples. So for example, 7 is a factor of 42 because 42 can be divided evenly by 7. We get a whole number, which is 6. Also, 42 is a multiple of 7. So 7 times another number, we end up with 42, which is 7 times 6. So there's a relationship between 7 and 42. So if you had that in your data display, you could make a statement about that. You could find that relationship. It really pays to know your times tables to find these relationships where there are factors and multiples at play. Some of them are quite easy, like 20 and 10. We know that 10 times 2 is 20, and others are a little bit trickier. We also can look at values as a proportion of the total number of values. So on yesterday, we looked at adding up all of the values in a data display to find the total number of values. So if, for example, we added up the total number in each of the columns in a column graph, or the total number of dots on a dot plot to find the total values. Then you can look at a single value, or you can combine values to make them a proportion of that total value. So for example, 12 out of 24 students study for 3 or less hours. 12 and 24, 12 is half of 24, so it represents half of the class. So we can say half of the class study for 3 or less hours. And lastly, you might just want to look at similarities between values as well. So for example, with our sporting one, 50 people liked rugby, but also 50 people liked basketball. So there was a relationship there. Okay, guys, thanks for listening. I'll join you tomorrow for our last lesson where we're looking at using data to make decisions. Hi, everybody. Welcome back. This is the last lesson for the week for Year 5 Maths on a Thursday for week 2. Today, we are looking at using data to make decisions. So today, we're using data in data displays to make decisions. To do this, we need to be able to read and interpret tables, column graphs, line graphs, and dot plots, which hopefully you're quite familiar with now. And then we're applying that data to a particular situation to make a decision. Okay, so there are lots of different ways to use data to make decisions. Today, we're really just focusing on looking at data to make decisions about what to do in the future. So to kind of plan for the future. So let's look at a column graph and a situation. So this is our situation. Bella has started a homemade donut business. She surveys 100 people about their favorite flavors. She expects to sell about 100 donuts a day. How can Bella use this data to plan for September? So she's planning for how many particular types of donuts she's going to sell in a day, and that will help her decide what ingredients she needs to buy, but also how much of those ingredients. Here we can see that 7 people selected strawberries, so that was the least popular, and 22 people selected cinnamon, so that's the most popular. Now, if there are 100 people here and she expects to sell 100 donuts in a day, we can think of this data as this is what a typical day would look like of donut sales. She would sell 22 cinnamon, 16 chocolate, 7 strawberry, and so on. So if this is a day and we want to find out what September is going to look like, well, we know that September has 30 days. So all we need to do is multiply this data here by 30. So once we've done that, we can put it into a column chart if we like, or you could put it into a table. And this is what the expected donut sales for September might look like. They might not look like this. Remember, this is very crude data. She's only surveyed 100 people. She might also sell more than 100 donuts a day, although that assumes that she has a limit of 100 a day. Maybe she only makes 100 a day. These are what we can maybe reasonably expect September to look like for donut sales based on this data. The more donuts she sells over time, she can update her data and she'll have more data to help her make a better decision about what's going to happen in the future. Now, nobody can predict the future with any absolute certainty, but the more data you have, the more confident you can be in your plans for what you think is going to happen in the future. Okay, let's look at a table now. So we've got Joe owns Cosmic Comics and he looks at his sales for 2020 for certain comic titles. He has to order the comics on a monthly basis, so he wonders how many copies of each he should order for January. So here we've got the table, and we've got Batman at 600 copies were sold in 2020, Spider-Man there were 420, Wonder Woman there were 180, and so on. And there's a total of 1,552 copies of these titles he sold in a year. So he's trying to figure out how many he should order for January. Well, if this is for the total year, then he can roughly say, well, there are 12 months in a year. So for January, he'll need to divide each of these copy numbers by 12. And that will give him copies per month. So here he can order 50 copies of Batman, 35 of Spider-Man, and so on. Some of these have been rounded up or down because they gave decimal amounts, but it kind of gives him a reasonable estimate of how many he should order for January. Now, this might not be entirely accurate. There might be more people who come in and go, well, I want to buy X-Men than just 5 people. But it still does give him an idea of, well, maybe I should just order maybe 10 X-Men comics because it's not very popular compared to Batman, where I should definitely order 50 or more. So it gives him some idea about the decisions he should make for his business for January in terms of ordering. Another way data can help us make a decision is that it can help us decide when to do something. So here we've got a line graph of the temperature in Tokyo in Japan, and it's got maximum temperature as red and blue temperature as the minimum temperature. And we've got a situation where Sam wants to visit Tokyo, but he can't stand certain temperatures. He doesn't like it if the weather is hotter than 20 degrees Celsius or colder than 10 degrees Celsius. So he's a little bit precious about the temperature. Well, here, anything that's above this line, this red line, so October, well, actually October is fine, April and October. Anything before April is fine, anything after October is fine, but it rules out these months in between. Now we've got to look at the temperature, the minimum temperature, so I use blue for that, and it can't be any less than 10 degrees. So here for April, it's fine. Anything before that is not good. And here we've got November. All right, so using that data, we can see when's an appropriate time or a suitable time for Sam to visit. We can see that this period here, kind of October, November, or roughly kind of October more or less. And here we can see it's this time in April, or the start of April, is kind of there's 2 times that are the most kind of comfortable for him to visit in terms of the maximum and minimum temperature. Now, this is just average temperature that's recorded in Tokyo over the years. You might have a year where it's really hot or really cold in one of those months, or the temperature fluctuates. So it's only not completely accurate, but it does give you some idea of when Sam could visit Tokyo and have a pleasurable experience. Now, before you go on to use data, one really important thing is to note is that past performance is not a reliable indicator of future performance. This means that just because something happened in the past doesn't mean it's going to happen again in the future. And this is particularly important for selling shares and investing. A company can do really well in 1 year and then do really terribly the following year. Or it can do really well for 10 years and then do really poorly for the next year after that. So this is actually a legal disclaimer that's put into a lot of products, particularly financial products, and there's laws around it to make sure that people aren't misled to think, well, this company did really well in 2020, so in 2021 it's going to do really well and I'm going to make lots of money. The same goes for any data as well. Temperature data can vary between years, sales data can vary, as we saw with customer data, like in terms of preferences can vary based, can differ to a sample. So it's really important to note that past performance is not a reliable indicator of future performance. Okay, and finally, we're at the main ideas for today's lesson at the end of this week's maths for year 5. So we can use data to make decisions about the future. We can add, subtract, multiply, or divide data to fit a new situation. We didn't actually look at adding or subtracting, but if you wanted to kind of make it larger or smaller, you can just add or subtract certain figures. But we really looked at multiplying to make, to scale something up to make it bigger, or to divide just to, find, for example, a month's worth of data compared to a year's worth of data. This line, past performance, is not a reliable indicator for future performance. And also something I haven't written down here, but just overall in general, these are very kind of crude ways of using data to make decisions. Ideally, you want to have the most accurate data, particularly with time series data. You want to have data for a long period of time, but there's always an element of uncertainty about what's going to happen in the future. So it doesn't mean that just because you have 20 years worth of data saying everything is going up and it's increasing, that the next year something catastrophic might not happen and kind of ruin that trend. Okay, guys, I hope you've enjoyed this week on data. If you have any questions, feel free to send me a message. I'm also going to post this as a PDF as well, so you can go back and have a look at the various slides if you need to. All right, talk to you soon and take care. Bye-bye.